Now for number 4, we have the rate of diffusion. Now the equation that we had for the Graham's law of effusion, now of course it sets effusion. Effusion is fundamentally different from diffusion by definition. Diffusion is simply going from high concentration to low concentration. And effusion is to run through a pinhole, but both involve the movement of the gas molecules. So even though it says the diffusion rate, you interpret the term diffusion rate as just how fast the velocity. So what do we know about velocity? Well, if they have the same temperature, they have the same kinetic energy. So no, same energy, but who runs the fastest? Yes, check the molar masses of each one, and whoever that is having the would have what kind of molar mass? The one that has the highest diffusion rate would have low molar mass. Fat people don't run fast. The equation, now, if you have to do an equation, you have this, okay? Now, speaking of this, I just want to quickly review the variant of the equation here. Now, sometimes they may give you distance. Sometimes they give you time. And this is where you want to pay attention to. Look at the subscripts. Okay. Now for distance and velocity, they would be pretty much the same thing, just replace the letters. But if you have time, you actually go in the opposite order, because the ratio has to be, has to make sense. So the more massive, think about B as a more massive gas, they're going to take more time to travel, okay? And the lighter mass would have less amount of time, okay? Whereas the lighter gas would travel a longer distance, and a heavier gas would travel a small distance. So that's how you make sense of all these arrangements. Okay. So make sure that you have all these arrangements done well for this Graham's law. And then among all these, so if you know the molar masses, this would be 16 grams per mole, 17 grams per mole. This one is 32 plus 14, so 46 grams per mole. And this is going to be 64 grams per mole. So it's going to be methane.